Imagine you are holding a scalpel. It feels precise. It feels sharp. You look at the edge glinting under the operating theater lights and you think, this is the pinnacle of human engineering, a tool so fine it can split tissue without a whisper. But you are wrong. You are terribly, terribly wrong. If you could shrink down, if you could become small enough to see what is really happening at the tip of that blade, you would be horrified. You would see a jagged, chaotic mountain range of steel atoms. It would not look sharp. It would look like a blunt, rusty saw. When a surgeon operates on a patient, from the perspective of the atoms, it is like trying to fix a Swiss watch with a crowbar. It is like trying to repair a spider web while wearing boxing gloves. We are clumsy. We are gigantic. We are tearing through delicate molecular structures with tools that are billions of atoms wide, smashing everything in our path, just hoping the body can clean up the mess later. And this bothered me. It bothered me back in 1959. And it bothers me now. Because I asked a question that made people laugh. Why not just swallow the surgeon? They thought I was joking. I was not joking. Let me show you what happens when you stop fighting nature from the top down and start working with it from the bottom up. Because at the bottom, at the level of atoms, there is plenty of room. Why are we so big? Seriously, think about it. We look at a car and we think it is complicated. A few thousand parts. Gears, pistons, wires, bolts. Impressive engineering. Now look inside a single biological cell. Millions of moving parts. Little chemical factories that break down food and turn it into energy. Tiny propellers that drag cargo along molecular highways. Information storage systems that make our best hard drives look like stone tablets. DNA, 3 billion letters of code, folded up neatly inside a space smaller than the head of a pin. And they all work. They work beautifully. They have been working for billions of years. So I ask myself a question, and I want you to ask it too. Why cannot we do that? Why cannot we build a surgeon that is small enough to go inside? Instead of cutting the chest open with a giant blade, instead of smashing through tissue like a bulldozer through a garden, why not just swallow the surgeon? You might think I am joking. I am not joking. I am talking about a fundamental shift in how we view the physical world. In 1966, Hollywood made a movie called Fantastic Voyage. They shrunk a submarine and a crew of scientists to microscopic size and injected them into a patient's bloodstream. The audience thought it was pure science fiction. But here is the thing. The physics problems that movie completely ignored are exactly the problems we need to solve. The water would not flow smoothly past a tiny submarine. It would feel like concrete. The crew would not see anything because light waves are bigger than they are. And the submarine would not glide. It would be shaken apart by the violent jiggling of molecules crashing into it from every direction. Hollywood got the dream right, and the physics completely wrong. And fixing that physics, understanding why the small world behaves so differently, that is where it gets really interesting. Because we are trapped in a way of thinking that says big is powerful. Bigger machines, bigger tools, bigger everything. But down at the bottom, at the atomic scale, that is where the real action is. There is plenty of room at the bottom. But to get there, to build this swallowable surgeon, we have to throw away your intuition. Because the world down there does not behave the way the world up here does. Let me take you there. Take your hand right now and wave it through the air. Easy, that's right. You barely feel the air. It parts around your fingers like it is not even there. Air is thin, Light. Practically nothing. Now imagine you are a dust mite. About 1/4 of a millimeter, roughly 1/100th of an inch. Tiny. Barely visible. The air feels thicker. Not dramatically, but noticeably. Moving through it takes more effort. Now shrink further, down to the size of a bacterium. 1 micrometer, 1/1000th of a millimeter. To a bacterium, moving through water is not like swimming. It is like crawling through molasses. Thick, heavy, suffocating. This is because at that scale, viscosity dominates. The stickiness of the fluid becomes the most important force in your universe. Not gravity, not momentum. Viscosity. If a bacterium stops swimming, it stops instantly. There is no coasting, no gliding, momentum, the thing that keeps your car rolling when you take your foot off the gas, essentially disappears when you get that small. Think about what that means for our tiny surgeon. We cannot put a propeller on it like a submarine. We cannot give it fins. It would be stuck in the thick soup of the bloodstream, unable to move, like trying to swim through wet cement. So how does nature do it? Because nature solved this problem billions of years ago. Bacteria have these remarkable little tails called flagella, and they do not paddle back and forth. That would not work in a world dominated by viscosity. Instead, they spin, like corkscrews. They drill through the liquid, threading themselves forward through the thick medium. Nature figured out the physics of the small billions of years before we even knew there was a small. Now shrink even further. Down past bacteria. Down to the size of a single protein molecule. Now the water molecules around you are not a smooth liquid anymore. They are individual objects. Bowling balls. Smashing into you from every direction. Constantly. Violently. Billions of times every second. You are not swimming anymore. You are being beaten up. Every molecule around you is slamming into you with random, chaotic energy. You get kicked left, then right, then up, then down. There is no pattern, no calm, no peace. This is the world our surgeon has to operate in. And this is where the real nightmare begins. Here is the first thing you need to understand about the world at the bottom. Water is not still. I know it looks still. You pour a glass of water and set it on a table, and it sits there. Calm, quiet, motionless. You think nothing is happening. That is a lie. That glass of water is a war zone. Every single molecule in that glass is vibrating, spinning, slamming into its neighbors at hundreds of meters per second. The water looks calm because there are so many collisions happening in so many directions that they all average out. From up here, it looks like peace. From down there, it is absolute chaos. This is what heat is. Heat is not some mysterious fluid flowing around. Heat is motion, jiggling, atoms shaking and crashing and bouncing off each other with furious, random energy. Let me give you a picture. Imagine you are standing in the middle of a football field, and the entire field is covered with medicine balls, those heavy exercise balls, each one the size of your head, and they are all bouncing off each other, bouncing off the walls, bouncing off you, from every direction, constantly. There is no pattern, there is no rhythm, just relentless, random bombardment. That is what it feels like to be a molecule-sized surgeon inside the human body. You are not floating peacefully through the bloodstream. You are being hammered. This is Brownian motion, named after Robert Brown, who noticed in 1827 that tiny pollen grains suspended in water danced and jittered for no apparent reason. He could not explain it. Nobody could. Searched it not for almost 80 years, until Einstein showed that the pollen was being kicked around by invisible water molecules. The jittering was the proof that atoms exist. So our surgeon is trapped in a thermal storm, being beaten from every direction by water molecules moving at the speed of a bullet. And you might think, well, that is a problem. How do we move through that? But here is where it gets beautiful. What if we do not fight the storm? What if we harvest it? Think about a ratchet. You know what a ratchet is. A wheel with angled teeth and a little pawl that clicks into place. The wheel can turn one direction, but the pawl catches it and stops it from spinning backward. One direction only. Click, click, click. Now imagine attaching a tiny ratchet to our molecular surgeon. The random bombardment of water molecules pushes it in every direction. But the ratchet only allows movement in one direction. Every random kick that pushes forward, the ratchet captures it. Every kick that pushes backward, the pawl blocks it. You have just turned chaos into directed motion. You have turned the thermal storm into an engine. Beautiful, right? Simple. Elegant. Take the random energy of billions of molecular collisions and convert it into useful work. No fuel needed, no battery, just the heat that is already there. There is just one problem. It does not work. I know. I can feel your disappointment. You thought we had it. A free engine powered by nothing but thermal noise. Something for nothing. But the universe does not give you something for nothing, ever. Here is what goes wrong. The pawl, that little catch that stops the ratchet from spinning backward, it is also a physical object. It is also sitting in the same thermal bath, which means it is also being jiggled by the same random molecular bombardment. Sometimes the pawl jiggles out of the way at exactly the wrong moment. The ratchet slips backward. And when you do the math, when you carefully calculate the probability of the pawl holding versus the probability of it bouncing, they cancel out. Perfectly. The ratchet spins forward and backward equally. No net motion, no free energy, no free lunch. This is the second law of thermodynamics, and it is absolute. You cannot extract useful work from a system at thermal equilibrium. The chaos gives with one hand and takes with the other. So what does this mean for our tiny surgeon? It means you cannot power it for free. You cannot just drop it into the bloodstream and let the thermal storm do the work. The surgeon needs fuel, real fuel, chemical energy, just like every molecular machine that nature has ever built. And this is where the story takes its most extraordinary turn. Because nature does not just use fuel to power tiny machines. Nature builds those machines atom by atom. And the way it does that changes everything we thought we knew about manufacturing. Let me ask you something. How do we build things? Think about it. How does humanity, with all our technology, all our engineering, all our billion-dollar factories, how do we actually make stuff? We take big chunks of material and we cut them down. We melt metal and pour it into molds. We stamp out shapes from sheets of steel. We carve, we grind, we chisel. It is like trying to make a sculpture by throwing rocks at a cliff and hoping something beautiful falls off. That is our approach. You start with a mountain of raw material and remove what you do not want. Top down, brute force, wasteful. Now look at how nature builds things. A single fertilized egg cell, one cell, smaller than the period at the end of this sentence, contains a complete set of instructions. 3 billion letters of genetic code. A program so sophisticated that it can take raw atoms floating in the environment and arrange them one by one into a human being. Not by cutting, not by carving, not by removing material, by placing atoms, precisely, deliberately, each one exactly where it needs to go. DNA is not a blueprint in the way we normally think of blueprints. It is a program. A set of instructions that says, take this carbon atom and bond it here. Take this nitrogen atom and attach it there. Fold this protein into exactly this shape. Build this molecular motor with exactly these components. The result? Machines so precise that they operate with single-atom accuracy. Molecular motors that spin at 10,000 revolutions per minute. Chemical factories that convert food into energy with near-perfect efficiency. Self-replicating systems that have been running without interruption for 3.5 billion years. We cannot do any of this. Our best factories cannot place a single atom where we want it. Our most advanced manufacturing is still, compared to a living cell, throwing rocks at a cliff. But here is the vision. And this is what kept me up at night. If you can arrange atoms one by one, if you can place every single atom exactly where you want it, you can build anything. Not approximately, not close enough. Anything. A material stronger than steel but lighter than plastic. A computer smaller than a blood cell. A surgeon that can navigate through your bloodstream, find a single cancer cell, and dismantle it molecule by molecule without touching anything else. This is not engineering as we know it. This is not building bigger. This is not building faster. This is building differently. Not top-down, but bottom-up. Not carving from bulk, but assembling from atoms. Not fighting nature's rules, but using them. The question is no longer whether this is possible. The physics allows it. Nature proves it every second of every day inside every living cell on Earth. The question is, can we learn to do what nature already does? And the answer, the one that will surprise you, starts with something so strange, so counterintuitive, that most engineers refuse to believe it the first time they hear it. The atoms do not want to stay where you put them. You would think the hard part is placing them, building the tools precise enough to grab a single atom and move it. And that is hard. But once you have placed it, you would expect it to stay put. It does not. Here is the thing about the nano world that most engineers refuse to believe the first time they hear it. Gravity is pathetic. At our scale, gravity runs everything. It keeps you in your chair. It keeps the oceans in their basins. It shapes galaxies. Gravity feels powerful, but shrink down to the size of a nanometer, a billionth of a meter, about 40 billionths of an inch, and gravity becomes irrelevant. Completely irrelevant. If you drop a tiny gear at this scale, it does not fall. It just floats there. Gravity cannot even compete with the random thermal jiggling we talked about. But here is what replaces it. Touch that floating gear against another gear. Just brush them together. Bam! They stick, instantly, like they have been welded together. You cannot pull them apart without enormous force relative to their size. These are van der Waals forces. The electrical attractions between atoms. Every atom has electrons buzzing around it, and those electrons create tiny, flickering electrical charges. Positive here, negative there, constantly shifting. And when two surfaces get close enough, within a few nanometers, those flickering charges synchronize and pull. In our big world, we ignore van der Waals forces completely. They are too weak to matter when you are made of trillions of atoms. But at the nanoscale, they are everything. Think about what this means for our surgeon. It cannot have normal bearings. The gears would weld together the moment they touched. You cannot use oil as lubricant. The oil molecules would be as big as the gears themselves. The machine would gum up instantly, like trying to lubricate a wristwatch with honey. So we have to design parts that never touch, parts that slide on cushions of electromagnetic force fields, parts where the stiffness is built into the very arrangement of atoms, diamond-like structures, rigid lattices that resist deformation even when van der Waals forces try to pull everything together. We are not just building small, we are engineering around forces that do not even exist in the world we are used to. And just when you think that is the hardest problem, the universe throws the ultimate curveball: quantum mechanics. When you get down to the size of a few atoms, things stop acting like things. They start acting like waves. Choose everything you know about objects. They have a position. They have a speed. They are here and not there. All of that starts to dissolve. At the quantum scale, particles do not sit in one place. They spread out. They exist in clouds of probability. And they do things that should be impossible. Imagine you are trying to build a circuit for our surgeon's brain, a tiny wire carrying an electrical signal. You build walls around the wire to keep the electrons inside. Good engineering. Standard practice. The electron looks at your wall and says, "I do not care about your wall," and it teleports through it. We call this quantum tunneling. The electron does not break the wall, does not climb over it, does not find a gap. It simply appears on the other side, as if the wall were not there. It is like throwing a tennis ball at a solid brick wall, a real, concrete, 6-inch thick wall, and occasionally the ball just appears on the other side. The wall is intact. The ball did not break anything. It just went through. Now think about what this means for engineering. How do you build a circuit when electrons keep leaking out of the wires? How do you build a tiny lever when the position of the lever is not a fixed point, but a probability cloud? You design it to be here, and the universe says, it might be here, or it might be slightly over there, or maybe somewhere else entirely. You see, we are not just shrinking a car. We are not just making things smaller. We are entering a completely new domain of physics, a world where certainty does not exist, where you cannot know exactly where something is and exactly how fast it is moving at the same time. We only have the odds. But, and this is the part that changes everything, this is not a dead end. This is an opportunity. Because if we can learn to control these quantum effects instead of fighting them, we can do things that are flat out impossible in the big world. We can build computers that solve problems faster than every classical computer in history running simultaneously. Quantum computers, machines that use probability itself as a tool. We can build sensors so sensitive they detect a single cancer cell hiding among billions of healthy ones. Not by cutting, not by imaging, by sensing the quantum signature of a single molecule that should not be there. The very weirdness that makes nanoengineering so difficult is the same weirdness that makes it so powerful. The rules of the game change when the players get small, and changing the rules is where the real advantage lies. So what does this swallowable surgeon actually look like? It does not look like a robot from a science fiction movie. I know that disappoints some of you. You are imagining a tiny metal man with a tiny metal scalpel swimming through the bloodstream like a submarine. Forget that image. Throw it away. The swallowable surgeon looks like a virus. It looks like a complex protein molecule. A folded, intricate structure made of atoms arranged with nanometer precision. It has no eyes. Light waves are too big for it to see. A wavelength of visible light is hundreds of nanometers. Our surgeon is smaller than that. Trying to see with light at this scale would be like trying to read a book using ocean waves. The waves are bigger than the letters. So how does it navigate? It tastes. Chemical sensors on its surface detect molecules in the environment. It can tell the difference between a healthy cell and a cancerous one by the chemicals they release. It does not see the tumor. It smells it. It does not have legs. It does not have propellers. It wiggles and ratchets through the thermal storm we talked about, using that same chaotic molecular bombardment that seemed like such a nightmare. The storm is not the enemy. The storm is the engine. And here is the part that changes the economics of everything. If I build a car, I have one car. If I want 1,000,000 cars, I have to build 1,000,000 cars. Each one costs money. Each one takes time. Each one requires a factory. But in the cell, the machines build themselves. The machines build other machines. Think about that. Imagine we build one tiny lathe, a baby lathe, smaller than a bacterium, and we use it to make 10 more baby lathes. And those 10 make 100, and those 100 make 1,000. In a few days, we have billions of tiny surgeons all working in parallel. We can manufacture them by the bucket load. The economy of scale becomes infinite. The cost of materials goes to zero because we are just using dirt, air, and water, rearranging the atoms into something valuable. This is the power of the bottom. This is what happens when you stop fighting physics and start using it. And before you think this is all just theoretical, let me show you what has already happened. We are just at the beginning of this. We have managed to write the entire Encyclopedia Britannica on the head of a pin. I said we could do that back in '59, and we did it. We have built motors the size of a single molecule, but it goes further than that. In 2016, 3 scientists won the Nobel Prize in Chemistry for building the world's first molecular machines. Tiny motors, tiny cars, and tiny elevators, all made from individual molecules. Ben Feringa built a molecular car, 4 wheels, each one a single rotating molecule, that could drive across a copper surface. Scientists have built nanostructures from DNA strands, folding them like origami into precise 3-dimensional shapes, shapes that can carry drugs directly to cancer cells. Lock onto a tumor. Open up. Deliver the medicine. Leave healthy cells completely untouched. In animal trials, these DNA nanorobots have successfully found tumors and cut off their blood supply, not by smashing through tissue with a giant blade, by navigating through the bloodstream, finding the target, and delivering the payload with molecular precision. We are not dreaming anymore. We are building. I stood at that podium in 1959 and said there is plenty of room at the bottom. 65 years later, we are finally walking through that door. Think about the implications. Heart surgery without a scar. Fixing a brain tumor without opening the skull. Just swallow a capsule. Billions of molecular surgeons enter the bloodstream, navigate to the tumor, and dismantle it cell by cell. You go home the same day. No anesthesia, no recovery room, no scars, repairing the damage of aging atom by atom, not just slowing down the decay, reversing it, replacing damaged proteins, clearing out cellular waste, rebuilding the molecular machinery that keeps you alive, so that we can live longer, healthier lives, not by adding machines to our bodies, by restoring them to what they were supposed to be. But this challenges something deeper than medicine. It challenges our philosophy. We tend to think of ourselves as these solid, continuous beings. You look in the mirror, and you see the same person you saw yesterday. Same face, same body, continuous, permanent. But we are not. We are piles of atoms. We are temporary arrangements of stuff. Carbon, oxygen, hydrogen, nitrogen, the same elements that make up dirt and air and water, just arranged in a very specific pattern. And that pattern is you. If we can master the arrangement, we can master our own physical destiny. We have been trying to be the master of the material world, but we have been doing it from the top down. We have been hacking at the statue with a pickaxe. Now it is time to put down the pickaxe. It is time to pick up the tweezers. No, not tweezers. Something smaller. Something that can hold a single atom. But here is the question nobody asks. If you can rearrange atoms to fix aging, to repair every damaged cell, to rebuild a body from the inside out, are you still you? If every atom in your body has been replaced, optimized, perfected by a machine smaller than a virus, where does the person end and the technology begin? Think about that for a moment. But here is what most people do not realize. We already replace atoms naturally. Every 7 years, most of the atoms in your body are different from the ones you started with. Your skin replaces itself every 2 to 3 weeks. Your red blood cells last about 4 months. The atoms in your bones are swapped out over about a decade. You are already a temporary arrangement that keeps rearranging. Right now, as you listen to this, atoms are leaving your body and new ones are taking their place. The nanosurgeon does not change this process. It just does it with intention instead of accident, with precision instead of randomness, with purpose instead of chance. And I find that not frightening, but beautiful. It is time to stop fighting nature and start working with it, to understand the jiggle, the stickiness, the weird quantum fog, and to use them, all of them, to build something extraordinary. So let's bring this all together. We started with a scalpel, a tool you thought was sharp, a tool that, under the microscope, turned out to be a jagged mountain range of steel atoms smashing through your body like a crowbar through a Swiss watch. And I asked a question that made people laugh. Why not just swallow the surgeon? They thought I was joking. I was not joking. We went down, all the way down, past the viscosity that turns water into molasses, past the thermal storm that hammers everything with random molecular chaos, past the stickiness that welds surfaces together, past the quantum fog where particles tunnel through walls and certainty dissolves into probability. And at every level, we found the same thing. Nature already solved it. Billions of years before we even knew atoms existed, life was already building molecular machines with single-atom precision, already navigating the thermal storm, already using the stickiness, the jiggle, the quantum weirdness, not as obstacles, but as tools. We do not need to invent something new. We need to learn what nature already knows, and we are learning. Nobel Prizes for molecular machines, DNA origami delivering drugs to tumors, nanorobots cutting off blood supply to cancer cells in living animals. I stood at a podium in 1959 and said there is plenty of room at the bottom. 65 years later, we are walking through that door. You know, a scientist friend once told me that a flower is less beautiful when you understand the biology. I told him he was wrong. So understanding the machinery inside, the cellular factories, the molecular signals, the atomic precision, does not diminish the beauty. It adds to it. The nano world is not frightening. It is beautiful, and it is waiting for us. There is plenty of room at the bottom. If this changed how you see the world beneath the microscope, even a little bit, let me know in the comments. What surprised you the most? What still feels impossible? Subscribe if you want more physics, explained the way Feynman would have explained it. No memorization, just understanding. And I'll see you in the next one.